Thank you for the invitation to be here at the Hausdorff Institute and to give this talk. So I've talked about this subject before. Some of you will recognize some of the diagrams and so on, because I've used them before. A good example is still a good example. But then there's some new aspects to it. So what's the context? So I'm quite flexible about the context really, but just to fix something, you have some Noetherian algebra, right, and it's graded. I can relax the grading. G's a finite group. Probably I want to stick to finite groups. But it's a group and it acts on a ring, right, in a nice controlled way. So the obvious example is a group that acts on a polynomial ring, preserving the grading, but there's all sorts of other examples. And everything we're going to assume is finite over some. Any module is going to be finite over this ring or some subring, right? This is just basic context. And so the classical theory, especially for a polynomial ring, you want the ring of invariance, right? And you calculate the ring of invariance, but I want to know what the ring looks like as a module. So, for example, a polynomial ring, this is the symmetric algebra on the module in degree 1. So you want to know what all the symmetric powers of that module are in some usable way. Right, so obviously they're determined, but how do you actually get at them? And so, right, that's the first motivation. It's just a natural problem. But the other one that motivated this quite a lot is if you calculate using a Lindenhof-Yonsel spectral sequence, you need to know the action of G mod H on the cohomology of H. You can complain that the cohomology of H is not a commutative ring, but it's close enough. And really, you have to, if you want to use this spectral sequence, you have to do the calculation for the action of G mod H on the cohomology of H in an explicit enough way that you can calculate this cohomology, and also you probably want to know some of the, well, what's left over of the ring structure, so some products, right? And it's not usually an easy problem. I mean, chromatic homotopy theory, you also have a group acting on a ring, so it doesn't fit into my context, but maybe you restrict to a finite subgroup, and then at least it's close enough to this context to be relevant. All right, so there's all sorts of other reasons you can have groups acting on varieties or schemes and other things. So, you want to know. For most of these problems, you need to know the multiplication as well at some level. So the big motivational example, which was calculated by Dieter and Karaguzian and myself quite a long time ago, was the following one, right? So you have a field of characteristic 3 and you look at the upper triangular matrices. Right, so we've got a group of order 27, and you can actually calculate, it's not so easy, this was done on Magna, so you can calculate the invariance on a polynomial. You have explicit formulas for them, and they're in degrees 1, 3, and 9, so I'm going to call them dx, dy, and dz. And so, right, the invariance is easy and well known. So, if you look on the dual space of V, which is the underlying variety, you can see that certain subgroups fit certain subspaces, which is going to be relevant later. And so then, here's a Magna calculation, which some of you have seen before, of the decomposition into indecomposable summands. Right, so here's the degree, and so degree 10, right, it's the sum of, the module is the sum of 5 things, and the number is the dimension, right? So 9 is not isomorphic to 9 primed, but it is isomorphic to the other 9, right? That's just the notation. So you can look at that, and you can see there's a pattern, right? The most obvious thing being that 27 is the free module. Right? But the rest is not so obvious. Quite a lot of things are divisible by 3, as you might expect. But what's the pattern? So this is the pattern. So, this represents multiplication by one of the invariants. So one of the invariants has degree 9, right? So you take this lot and multiply it by the invariant of degree 9, and you get this. So you multiply again, and you get that, right? And this part, all right, this part, you can multiply by the invariant of degree 9, or the invariant of degree 1, which was the x, and you get those, right? This part is the one of degree 9 and the one of degree 3, and this one's all of them. Right. So already you're learning a whole lot, right? Well, if you believe the pattern, right, that projectives are going to dominate, and so on. And of course, if you're doing a cohomology calculation, that's probably good, because you're not too worried about this part. So, okay, so what does that mean? Right, so this is basically what I said, right? But the point is these, let me have to go back. The second to right block, if you looked at it, it's spread out by 2 variables, and it's projected to the relative to, second to right, is projected relative to the subgroup which fixed a certain subspace, right? And so the number of variables that you spread out by and the dimension of the fixed point set of the subgroup with respect to which this thing is projective correspond. So, right, so there's a pattern, we want to understand this pattern. Okay, so, right, this is very basic commutative algebra. This started off as a very general talk for something else. So, in particular, we get to look at dimension, the dimension of this module. Everything's, for example, a module over the invariant ring. Everything's going to be a finite module over the invariant ring, so you can talk about dimension and depth. So, the dimension is just telling you how many of these variables are spreading out the thing, so how big it gets as the degree increases. The depth is a bit more subtle. It's how many variables it can be free over, right? And so, in particular, you'd like things to be co-Macaulay, where the depth is equal to the dimension. And this means it's really easy to calculate all sorts of things, because it's like having a free module with a finite basis. And so you can do all your calculations with respect to this basis. You might prefer a slightly more sophisticated definition, but that will do for the idea here. And so all those pieces that I showed were co-Macaulay because they were free over some polynomial generators. But you can do other examples, and this will in fact happen for, say, upper triangular matrices, but it doesn't happen in general. So that's an obvious question that I was looking at. Well, when are these pieces co-Macaulay? And so I said something about co-Macaulay. So there's a famous quote by Melvin Hoxter. He wrote somewhere that life is really worth living in a co-Macaulay ring. And then he must have got some flack for this because he changed it. So, okay. Okay, so I want to understand more about this. So the classical thing to look at, particularly in characteristic 0, is called the covariance, which has rather confusing notation. So KVM is K of V, but then you tensor it with some module and take the invariance. So it's essentially it's polynomial functions from V to N. And people looked at that, and in fact, in Stanley's book, in characteristic 0, these are all co-Macaulay dimension. In V.
Did the polynomial functions from V start with that?
No.
K of V is polynomial functions on V. It's
Oh,
not the
okay,
symmetric
it's not the
calculation.
polynomial ring.
It's the-
Okay. Yep.
K of V is the symmetric functions on V star.
Yeah. Good.
Okay. So, but yes, this is very confusing. Usually takes several iterations to get all the stars right. So, but I'd rather turn this around. So now I do want a star, right? It's hom actually from, it's the same as hom from M star to K of V. And so I prefer to look at hom of something rather than tensouring and taking invariance. So, and it's a nice functor, right? So we're going to look at various functors related to hom of M into the thing, right? So if you take M to be the trivial module, that's the invariance. Okay, so here's some functors you could look at apart from plain hom. You could look at some x hat, right? Or you could look at hom from the projective cover of a simple. That will give you the multiplicity of the simple as a composition factor, right? There's all sorts of things you could look at. Okay, so I'm interested in indecomposable summands. Why it's good for the cohomology calculation, but also because anyone who studies representation theory, it's somehow programmed into them to want to know what the module is as a sum of indecomposables. I mean, it's often hard even to get people to even prove anything without first writing the module as a sum of indecomposables. So, and clearly that's one of the best things you can do. So I'm going to look at what I call hom plus kg, you can call it whatever you like. And in terms of category theory, you just reduce modulo the radical of the category. So if you don't know what that means, or you want something a bit more concrete, you could quotient out the ideal of all homomorphisms which are not split injective. Right, it looks a bit strange at first, but this is what it is. And you wonder why it's called the radical. There's all sorts of reasons, but one is on endomorphism rings, it really is the radical. Right, if you look at all the homomorphisms, all the endomorphisms of an M, then the radical is the radical. And it also, it's the F-span of, it's the K-span of anything that factors through an indecomposable module that's not M. So this is sort of classical category theory or representation theory, but the point is it commutes with direct sum, and you know what it does on, it picks out one indecomposable, right? So it counts the number of times that M is a summand, right? Which is sort of a problem I set at the beginning. I wanted to understand this as a direct sum of things, but there's a bit more there, because in fact this is a finite module over the ring of invariance, for example. Right, so you've already seen some structure on these multiplicities. They're not just random numbers, because they correspond to the graded dimension of a finite module over a Noetherian ring. Yeah, which is what it says there. So, oh yeah, and you can also look at, I like this one, though I'm not sure why, you can do it you can look at trivial summands. And so in this sort of context, I mean, trivial summands don't form a ring on the nose, but in this, defined this way they do. You can easily check that thing as a ring. Okay, so, and so there was some idea that in characteristic P this might be a good thing to look at, right? Though I actually don't know what to do with it. Okay, so now we come to the Brauer construction, which has come up before in the talks of Paul and Martin. So this is a definition that works even when you don't have a P group, but let's assume you have a P group to make things easier. And the point is, for for G sets, permutation modules, it calculates the fixed point set. So, so now we're in the dual problem again because k of x means functions on x. Right, so rather than linear combinations of the elements, but of course it doesn't really make much difference. And so this now gives you the fixed point set, and this is very easy to check. Right, you take one orbit, right, and so you look at the fixed points as a module, that's the sum of the elements, or if, well, since we're doing functions on x, it's the constant functions, right? And then you modulo out by the image of the transfer, and you can either hit this constant thing or not, depending on what the stabilizer is. Right, you should just try it yourself, right, on one orbit, and then of course it's additive, so it applies to finite G sets. So, and that's for the P group. Right, so if it's not a P group, you're going to get everything that's fixed by some conjugate of your P group. Is that right? Yeah. So, and again, it's finite over the ring of invariants, so you can ask the same sorts of questions. Okay, so since we have a ring, you can try to look at the fixed point sets in the geometry. So this is basically how you get the fixed point set in the underlying variety. And so for a P group, you really get fixed points, and if you're looking at functions on V, right, you know what fixed points are, right? You have a vector, you have a representation of a group. Fixed points really means a fixed point subspace, and if you knew anything about V, you probably know what this is. So this is something you can compute in any reasonable case. And so sort of untangle this. So so here's a theorem. So you have a whole lot of things, right? There's the Brauer construction, there's the trivial Symonds, and then there's things from algebraic geometry, which basically are is the fixed points. Right, I consider it as a subvariety of the original thing, or as the quotient. And you get universal homeomorphisms of spectra. So, so the definition apparently is that they homeomorphisms that remain homeomorphisms after any base change. But this is what you might be more familiar with as an F isomorphism, say Quillen's F isomorphism theorem.
Could you just repeat what I is? I forgot.
Sorry?
Could you repeat what I is? I forgot.
Is calculating everything that's fixed by the P subgroup. So it's a
Okay.
yeah.
No, I is equal to the intersection of IH. And what is that? Sorry,
IH is the thing above.
Ah,
It's really not doing anything very.
okay.
So the intersection is giving you the union, right? This is the fixed point. So, and I don't know, I call it a universal homeomorphism because that's what's in the Stacks project, and I just copy what they say. But it's actually quite interesting. Does anyone? So, the characteristic P for Noetherian rings, this is equivalent to. Oh right, I didn't say. So So in terms of rings, this means the kernel is locally nilpotent, and for any element in the codomain, some p to the n power is in the image, right? So it's also totally algebraic, but in fact, if you're not in characteristic P, does anyone know what the universal homeomorphism corresponds to? I had to look it up, but it's actually very strange, so we've got time, I'll repeat it. So you have, you just have just an extension of rings. Right, that's all. And so then the following equivalent one is that is one of these things. And the other one is the algebraic characterization. And so it says every finite subset is contained so the finite extension one is such that for each I, so I is 1 up to n, you have one of two things happens. The first is that bi squared and bi cubed are in the previous one. So or there's a prime number p and pbi and bi to the p in the previous one. So it's not. So you can see at least the isomorphism fits into this. It's not terribly relevant to what's coming up, but I was amazed when I read that. You have, on the one hand, you have this very natural thing in part 1, and you have this seemingly random condition in part 2. Okay, but that's just what it is. Anyway, I'm going to stick to characteristic P. So,
So your first one was this Brauer quotient, right? And
yeah.
Then,
And the second one is the trivial summands.
oh, okay, yeah. So that's why it factors through.
Yeah. So the first thing is to show that these morphisms exist, which isn't that they're well defined, right, which isn't terribly hard. And then we have to ask why. Why is this true? So you've got to construct this F isomorphism. So if you look at the first two, they're naturally onto. So it's just about the kernel being nilpotent. And the way you do that is, well, the slickest way is you take a maximal ideal of the invariance of SG and reduce modulo that. And then you're just looking at one orbit. And because you're just looking at one orbit, the result is true because it's true for G sets. And so now you've proved it modulo every maximal ideal, so you just say null Stellensatz and you get the result. And so then there's the one at the right, right? Why is it, what happens at the right? So you take, so at the right, you're going to take, say, y plus I, and you want to lift it to something in that's invariant, in S that's invariant. Right? And the image has to be some power of it has to lift. Right? It's got to be a p power. So the obvious way to lift something like this, or try and lift it, is to take an orbit product. Like norm or an orbit product. But if you do that over the whole group, it's not a p power. So you can take the norm from 1 to p, so p is a series. Of y. Right, so that's only fixed under p so far. But if you map it down here, because this is invariant under the group, then when you map it down here, the norm isn't going to do anything. So this maps to y to the p, well, plus r. Right? But now you're only invariant under, we can't put g here because then it's not a p power. Right? And we really want something to be invariant under the whole group. So, but now you can just do the trace from p to g and maybe whatever. The inverse. Right, and so you've lifted it. So that's why you get an F isomorphism. Universal homomorphism. So so this is just trying to identify what the geometry tells you you're looking at. So, so for a P group and KG module, you really get, I'm mostly only going to look at the dimensions of these pieces. So you can see that the dimension of the Brauer question, or the dimension of the trivial summons, is the dimension of the fixed point space on the module. Right, which is not entirely obvious because one's sort of back ring theory and one's not, for instance. And if you want, I'm not going to go into this, but you can also work relative to other classes of subgroups, like they asked yesterday, I think. Right? You don't have to look at all the subgroups you could do. So you go if you work relative to the trivial subgroup, you're looking at sort of Tate H0, for example, and you get the P singular space. Right, so all the points that are fixed by some elements of order P. And so here's an example where maybe you can see something. So this is another one of my favorite examples. So this is a cyclic group of order P, and having drawn so much on that picture, I forgot to say perhaps the most important part, which is what the action is of this group. So x goes to x, and y goes to y plus x. And so, what have I done? It's supposed to be that. So you can write down the invariants, right? The invariants are x, so it's invariant, right? And this thing, which is the orbit product of y. And that's all the invariants. And so now I would like to take a monomial basis, but that doesn't work. So everywhere I have a power, everywhere you'd expect to see y to the p, I replace it, well, by dy. So right, obviously x is going horizontally, y is going vertically, so the degree goes diagonally, right? And so up to here I'm just using x and y, but from here up I'm using one power of dy, and then increasing with y, so in this one. And so why? It's because all these bits, this bit below the y to the p line is actually a submodule over the group, right? And so if I then multiply it by dy, which is invariant, I get another submodule over the group. Then I get another submodule over the group, and that's this thing, right? The whole thing is this bottom p rows spread out by dy. And this works in more generality in bigger polynomial rings, and is why it's much easier to work with polynomial rings, or at least why I can prove a lot more for polynomial rings. So But you can see in any degree, and you can see in any degree, you're getting projective, the big, like every block that is sort of written like that corresponds to an indecomposable summand. So there's lots of these projective indecomposable summands, right? And then there's, in any degree, there's just one extra, which is a bit shorter, and that's indecomposable but not free. So, right, that's the complete calculation. But what does it mean in terms of this picture? So, if you do the Brauer quotient, right, you'll find the trace only kills the circle of the projectives. So you'll be left, you go up with the dy's, and you're also left with powers of x's up to x to the p minus 2, x to the p minus 1 being a trace. And so you've got these extra bits on there. So then, if you look at the invariant summands, well, it's clear from the picture they were just the little blocks of size 1, so it's just those, right? So you lose, this is still potent, and you lose it when you go from here to here. This is the same, and then if we go back to k of Vg, so this is just k of y, and you can see this mapped into this, but its image is the pth power. Right, so that's really what the theorem is telling you. And so this generalizes to other polynomial rings, but only to polynomial rings. So most of the results about depth are only about polynomial rings, as maybe you'd expect. So a certain amount tensors off, right, which has something to do with a fixed point set. And so notice here, it's the dimension of the fixed point set is R, so these are the variables that just tensor off. And so you sort of get depth and so on, everything for free. Basically, every R things just tensor off. The other bit is not, but this U is not really a ring. That's the problem. Right, it's just a module. And so, right, there's a notation, but any indecomposable module has a vertex which is the smallest p group that it's induced up from. Right, essentially, I mean, or a summand of something induced up from if you're not dealing with p groups. And and this controls a lot of its representation theory, or indeed geometry here. So this is the best I could do. So if you want the multiplicity of m inside k of v, it's less than the dimension of the fixed point set of p, so the vertex. Right, so in particular, I mean, what does that say? So for example, if you take a projective module here, right, the vertex is the trivial group, so it's the whole, you get the whole of V here, which is maximal possible dimension for a subthing of kV, right? But if your CEDO may have quite small vertex. So, I mean, fixed point set, so this will become very small. So none of this is really doing any calculation for you if you had a cohomology calculation in mind, but it's giving extra structure and showing you what you might expect. And here I get somewhat stuck. The depth for a polynomial, and this one is true in great generality. You don't need polynomial rings. The depth thing is difficult. I don't think this is the best result. It's the best I could get. So you need the inertia subgroup, so that's the stabilizer of the CR. And it was quite hard to get. And in fact, to get from I down to IP was the biggest problem. And eventually I had to use some of this, the theory of Auslander and Reitman and functors and so on, because a lot of their stuff is all about these functors. And I can get down to there, but this isn't probably optimal. I don't know what optimal is. But you have this annoying thing that keeps coming up. You always have to keep saying, if this is not 0, then that. Because of course this module might not occur at all. Right? And you have to be careful here because there's a question, what is the depth of the 0 module? And this is a problem. If you look at the Stacks project blog, they had a long discussion about this. And it depends, and their eventual conclusion was to put in a comment saying if it's not 0 every time. Because it was easier than dealing with this discussion. Because what is it supposed to be, right? You'd expect it might be 0, but anything that's like finite, say finite as a vector space has that's depth is 0, right? So the 0 module wants to be smaller. And so there's a paper by Huneke and Wiegand where they use the definition that it's -1, because -1 is less than 0. Then they had to publish a correction at the end because their theorems went wrong or the proofs went wrong and something turned out to be the 0 module, right? It's like these problems of what happens if the set is empty. And so they retracted and reformulated something, and they decided they were going to go with infinity. And in fact, infinity is probably the one that wins, but it's easier not to say. So it depends on your definition of depth. So the
Infinity, not minus infinity.
No one goes for minus infinity.
No one goes for minus infinity.
I was looking for someone who I was actually trying to look for somebody who said minus infinity, right? I wanted to know all the possibilities. And I'm sure somebody must have gone for 0, but so it depends on your definition. So the depth is really defined in terms of a regular sequence. So you have a module M, and so a regular so it's R module. And so you want, well, x1, you want x1 to be a non-zero divisor on M, which just means if x1 m equals 0, implies m equals 0. Right? And then you want x2, the non-zero divisor on m over x1m, and so on, right? And you want to see how far you can get, and the furthest you can get is a regular sequence, and but if you look at most commutative algebra textbooks, certainly ones written in English, you want 1 over whatever it is, x1, well, I don't know, wherever you've got to, and it all depends on this. Right? And I said because if you're French, you don't put this. And that's why you get a different answer. Because if you don't put this part, anything is a regular sequence, right? You could take 1, 1, 1, 1, 1, or you could take 0, 0, 0, 0, 0, and you keep going, and you get infinity. Right? And also, infinity was Grothendieck's choice, and who's going to contradict Grothendieck? So, and mostly it works because mostly if you're just looking at depth, you have inequalities, right? You have a short exact sequence of modules, and the depth in the middle should be less than or equal to the maximum or the minimum of the depths of the other sides, right? And infinity just makes these inequalities true for silly reasons, and so you're safe, right? But of course, the most important property of depth really is that depth is less than dimension. And that's completely messed up. So anyway, that was another aside. So
see, that would work with minus infinity.
It would, yes. I rather like minus infinity, but yeah. Anyway, that's the opposite. That's the opposite of Grothendieck, right? So it's dangerous. And the other ones, the other inequalities will get wrong. So. So you just don't do it. So, so for example, this is enough to show that some things are Cohen-Macaulay, but not everything. Right? In fact, not everything is Cohen-Macaulay, even for a polynomial ring. And there's lots of examples of why it's not Cohen-Macaulay. What's the easiest one? I can just squeeze second blackboard after all. You could do P equals 2, G equals C2, and let's get K of, well, K is a field of characteristic 2. So 2 copies of the free module. Then you get things that are not Cohen-Macaulay. So what comes next? And I did wonder about Gorenstein. They like these Gorenstein invariants. So maybe the trivial summands of Gorenstein seem not unreasonable, but it's not true. So. And there, the example is P equals 3, slightly below the 3, but now you want V to be the modular of dimension 2, and you look at K of V plus V. And it's the same story as maybe in Nick's talk, right? The way you get these counterexamples, everyone gets counterexamples in this, is you just look at something like n plus loads of copies of n, and you let little n get big, if it makes sense for little n to get big, and then you get the counterexample, and that's what Nick used in his talk. Right, and then all counterexamples in invariant theory seem to come from this. I mean, why? I think just because what else are you going to do, right? It's your first choice. And so, but, right, so it's not true for hom plus, so you change the functor and then it becomes true, but maybe it's not quite so useful. So this one, if you do the Brauer construction of hom, that's hom modulo traces from proper subgroups, if you're a P group. Right, and then you do get it. Everything's nice and comical. Here, P should be the vertex of n. No, it should be the seal. And a lot of this, the dimension stuff applies to a general ring. Right, so the number of summands is determined by the P's, definitely the vertex now. And so if you want, you can take modules over your ring, right, which still have a group action, and do the same sort of thing. And again, they're going to be, this is going to be a finite module over something which you've already controlled. So you can control the dimension. So I think it's this. I made this up just for this talk, so I think that's right. Just because this is a module of something without the f, and you know the dimension of that. So you can control a lot of these things. So a few other points. Yeah, I don't know how far this can go. I mean, I think for general rings, depth is hopeless. So you want other things to look at apart from dimension. I'm not sure what, or exactly what you can prove. So to finish off with, there's a few other things. So for K of V, in fact, even though there's infinitely many degrees, so you might get infinitely many different indecomposable modules, you don't. So that was originally proved by Deepan, Haragousian and myself, but there's other proofs as we can do now, because the first proof was very calculation, involved really big calculation. But it's not true in general, right? And So if you do other rings, I think the counterexample to that is, again, something simple. So the first group for which you might get infinitely many different indecomposables is C2 cross C2, because cyclic groups can't happen. And so you have to have some ring, and it's, I can't remember whether it's 4 variables or 5, but this one won't do any harm. But the relation is xy minus or plus zt, since we're in characteristic 2. And I know when I talked about this, so I showed this to Shrikant Iyengar, who just said, oh, well, that's the counterexample to everything. But you have to take the right action of C2. Some of them it works, some of them it doesn't, even on that rate. And the other thing is to do with Casanova-Moffat regularity, which is something I proved most of these do, or dealt with, most of these do with invariance. As a reg is the Casanova-Moffat regularity. Strictly speaking, from what I'm about to say, I want H-reg, which is a slight variation which I used in the paper. But it's, so I don't want to go into what it is. It can be defined, say, in terms of local cohomology or projective resolutions over a polynomial subring. But what it gives you is bounds. For a module, it gives you bounds on the degrees of the generators and relations, which is what we want here. And so, so you say you want to calculate this multiplicity module for M, right? And so now this, you don't need to, you need polynomial, well, it doesn't even have to be a polynomial summing, it's just generated by some things. They don't have to be algebraically independent, but because this is smaller than, the dimension of this is smaller than the dimension of SG, you can probably just get a small collection of things here, right? So you try and make this as small as possible, and then this thing is generated as a, what was R? Yeah, R is this. It's generated as a module in degrees at most that, right? So you've completely determined it in those degrees as a module. And if you do it slightly differently from the definition of regularity using projective resolutions, you see that if you don't worry about the module, you just worry about the graded dimensions. If, say, you get a computer, or you, or a computer or anything, calculates up to this degree, then you can, it's an easy calculation with Hilbert series. You just can write down what the Hilbert series is for in every degree. So what looked like it's an infinite problem, right? Calculating this, in principle, yeah, I mean, in some sense this is spotting the pattern, right? You spot the pattern correctly up to a certain degree, then you have spotted it. You spotted it correctly. There's a certain art in choosing these, how you find these DIs, and maybe you want to extend a field, and then you can get ones in lower degrees and so on, right? But again, it doesn't completely solve the problem, but it does show that actually this decomposition problem is feasible in some sense. So I think I'll stop there.